Morning, everybody. How are we doing? What a beautiful day outside, at least here. I hope you're having fun where you are. We are going to have a webinar today on irrigation calculations. This will be pretty interesting. We just thought it'd be fun to do kind of a deep dive into the calculations and kind of understanding, why we do things the way we do and where to look when you think things are wrong, and this I would classify this webinar as a direct offshoot from just simply tech support. So, we kind of sit down, we look at these tech support issues and what are some common questions that people have. We're like, you know what? Let's be proactive and let's have a webinar that kind of addresses these really common questions that we get. I got a couple super quick housekeeping items for you before we get rolling. Just want to mention there is a Q&A button at the bottom of your screen. Stands for questions and answers. And I would recommend clicking that right now because you'll get it situated on the screen. It'll make it a little quicker for you to type a question. But note, you're going to be able to see the answers that we type to other people's questions. So it makes a fun companion while you're watching this live with us. And although this is live, it is also being recorded. So if you miss any bit or you want to show someone else afterwards, it's going to be up on the website later today. And that is pretty much it. I think we'll pick up the trash outside. I hope that's not too loud. Perfect time for me to just hand this over to Jake. All right, Jake, let's take it away.
Very good. Thank you, Jer. Welcome, everybody. We got a full house today. I'm glad you're all here so that you can teach me about irrigation calculations. I am Jake Lott, irrigation specialist. I've been doing irrigation for well over 20 years now. Love it to death. So I do kind of geek out on this stuff, but also am a sponge and love learning new things that I don't know. So hopefully we can, cater to the masses here, and all questions are needed here. Would love to know, what questions you guys have in regards to the calculations themselves, obviously, but what we are going to focus roughly around is from a sizing perspective and just the tools and stuff that we got going on. So the outline, general concepts, really how pipe sizing works, just a very simplified overview of that. And then just as you are designing, things to consider, and then where to actually find and account for those things. And then, of course, please, questions. We're just going to get right into it. Did a little power tip ways back on the mechanics of pipe sizing, and it was a fun little graphic of how water works in the simplest of terms. And it's very simple. If you speed the water up, you get pressure loss because it's trying to push all of that flow through a smaller pipe, which means that you're going to have a higher friction loss. If you slow that water down, you actually increase your pipe size because you are getting less friction loss. So these are the main concepts that we really want to kind of focus on through this whole process and the equations and stuff that are happening. It's a very simple as you break it down. I've come to find that it's very, very simple on that standpoint. So considering our source information, this really is only applicable when we're sizing the main line. Okay, our water source is what's available. At the end of a design, you're always going to need this information. But during the design, you're welcome to place heads and size the valves and just do the whole design. But being able to have that conversation about what those numbers are, what we have available, what we even need is going to be really important so that we're not getting to that end and being confronted with these negative numbers, like why are we exceeding what we have? Well, if we have that conversation up front, we kind of know how to plan the rest of our design stuff. So, it leads right into this buffer of, what should we have and left over kind of a thing. A little tip that I always like to tell people if they're, saying that, what, I don't know what the source is, or I'm not given those numbers. Like, how do I know what to put there? If you set your water source as a custom, you can actually zero out the flow and the pressure and get a negative value. And those negative values are going to be what the demands of the system are. So now you can take those numbers and kind of have that educated conversation with the client or the city or whoever it is to say, hey, this is what we need to work. And then you can actually add that additional buffer that you might need on top of it. I know a common number is 10% of what you have available should be what you have in residual. So if we had a static pressure of 80, we should have an additional 8 pounds to work with after we're all is said and done. So when it comes to the pipe, obviously the charts that we are very, very familiar with, or should be very familiar with, it correlates to sizing those laterals and those main lines. And what we want to kind of pinpoint, and we're going to hammer this in quite a bit through these next little slides here, but we got to understand that the velocity is literally the only variable to adjust in this whole grand scheme of things. And that dictates what size of pipe we're going to have, because the flows are actually fixed. So we know what the flows are for the stations. We know that that's not really going to change from a zone perspective. So that means the only other side of things that we can actually change is that velocity. Now, you might have different ways of cross-checking, have like a little Excel sheet or something like that kind of helps you determine what that pipe size should be based on those. And this is the formula that is being used to derive that. It's very simple. It's two values. It's the flow and the velocity, and that gives you your inner diameter. So there's the equation right there. We're not going to go, hammer that too much, but that is literally all that is required to understand what the diameter actually is. So if you compare your own little chart thing, if you're going to do the formula itself, to what the pipe charts show, you can see that I've got a flow of 9 GPM and I want it to be running at 5.4 feet per second. Well, I'm going to need this inner diameter pipe in order for that to operate that way. So if we start to understand these concepts of knowing which values that we're looking for which size of pipe that it's going to be given, it's straight up math at this point. And we have tools in Land Effects that really help you with that. So a tool that I'm going to try to show off in the live demonstration is that flow zone, the little image right here to the left, is a very comparable. If you had your own little calculator, this guy's doing the same thing, but it's just nice and built into the system. And you can use that as a cross-check to see what size you're actually anticipated to get based on the flows and the speed. And this is why when we're doing sizing of our pipes, whether it's the main lines or the lateral lines, that the only variable that we really need to focus on, and obviously there's a couple other options to help buffer that or cross-check and limit what we're doing to the system, but the only variable here is that speed, because we know, or the system knows, that this zone that you're trying to size has a set flow, and you are basically just now altering how fast it is going and allowing the system to choose the pipe sizes appropriately from that. The equipment, this is really determined by a lot of things. Obviously, our site conditions, whether it's elevations and soil and sun exposure and all that stuff, but really client expectations and stuff like that, all of these things should be really considered heavily in that discussion right up front. We should be looking at the equipment that we're picking and looking at those pipe charts, looking at the performance data charts, looking at all of those little pieces so that we are making those educated decisions on, hey, what size should I be using here in this condition? This is really important when you're just going through that process of picking that equipment, and to be able to then have that discussion with the client, being able to add the equipment that you think you want to use, run a schedule of entire pallet, and have that conversation with a client for approval. This is going to really mitigate the whole, headache down the line of, oh, I picked the wrong stuff, and now I'm battling with this either out of its performance range functionality or whatever it is, to be able to, dial those things in even before starting. And the other thing to note here at this level of picking equipment is understanding that we have schematic, and schematic is a really good place at this stage of things because it's way less effort. And again, if we are understanding these calculations, we can set up our schematic areas to function the same way so that we can simply place hatches in areas to generate flows to understand what kind of head types and valve types and how many zones we're going to need at a very basic level or a high level, so that we're not sitting there wasting all the time placing everything just to have to redo it. So sizing a system, this is just going to be a quick refresher on what the typical process is. And so I'm hoping that for everybody here, we obviously have the basics of how we generally are sizing a system, and that is from the furthest head back through the lateral pipes to the valve, and then we're taking that value from the valve and we're doing that same thing through the main line back to the POC. So understanding that, this is our best friend right here, right? This is what we always go to when we're looking at that that chart, making sure that we've picked our right pipe class and we are zoning things and we know what our flows are for the sections of pipe, and we're doing all of that fun math, right? Well, this is, again, the formula for determining that pipe size. Now, when we're doing this, sort of call it the old-fashioned way, we are determining those pipe sizes, but sort of at the same time, we are looking at the velocity, the friction loss at the same time, just because this pipe chart is sort of wrapping it all together. But if we're kind of understanding this, it happens in two buckets. We are looking at how much flow we have, and we are looking at how fast we want it to run, and we're choosing that pipe size. At that point, it's obviously then that we need to figure out that friction loss, and that's that other bucket. And I'm going to admit here, for the longest time, I was very afraid of this formula, and not understanding, yeah, we use the Hazen-Williams formula, but what does that actually mean? Like, I just look at the pipe chart and yeah, that is what it is, right? Well, if we're going to break this down, it's super easy. And I created, spreadsheets back in the day to be able to help cross-check, like, okay, these are the values that I need to try to figure out. What is that pipe coefficient? The smoothness of the inside of the pipe. What is the flow going to be, and what is that inner diameter? So if you know those three pieces, that is literally all we need. And I think there's a misconception of going, oh, hey, the Hazen-Williams formula, it's all about the velocity and stuff like that. Well, it's actually a little bit backwards from that. I just need to know my coefficient, my flow, and my diameter. Well, how do I know my diameter? Well, that's where my flow and my velocity come in. So it happens in two different buckets. But if we're going to break this down and do this little example here, we've got a red number, our blue number, and our green number here. So it's simply three things. If I know my red number and I know my flow and I know the pipe size, because I know the flow and my velocity, I can determine what my actual friction loss is going to be. So this formula really breaks down into these three different buckets and follows the pipe chart perfectly. And that's how these pipe charts were derived. And it's very easy to now navigate this and determine what pipe you're going to need based on this. Now, the tricky part is this. We can follow these pipe charts for what they are given, but what if it falls outside of this range? What if it's 10.5 gallons, or what if it's 8.2 gallons? You know, what do we do there? Well, if we take that concept and just know that we have a given flow and the velocity that we want to stick with, it's still going to give us our inner diameter pipe, which means that we got to fit it into what size is available. So from there, where does that actually play into when it comes to using software? So our design pressure, our emission data, the performance data, that all happens when we're adding that equipment to a project, okay? Every piece of equipment that we're picking from any manufacturer is going to come with all of the data pre-built into it, respective to what we're given from a performance chart, okay? And so picking that design pressure is setting that benchmark of, okay, this is what I need to start accounting for from that furthest head, and working it my way back through with the given flows per head and how many heads there are and what the length of the pipes are. All of that stuff gets thrown in to then go, okay, based on that, all of my classes of pipe that I'm setting up for my laterals, what sizes am I, allowing the system to use in the performance of that velocity, and what is then, when I get back to the point of connection, what do I have available? What is my source data set to, and how is that cross-checking? So the final cross-check that we're really after here, again, somewhat of as a reminder, is a critical analysis. And a critical analysis isn't necessarily, I mean, we obviously want to know globally how the system's doing, but our focus is, what's our worst case scenario? And that is our cross check. So to be able to run this critical analysis and understand, what pressure I have available at my point of connection, is there any elevation differences, to, okay, what's my maximum station flows? Am I in the positive there? And then the most important thing, which is pressure, and what station is causing the worst case scenario for that pressure. And we can cross-check that single critical analysis with a valve schedule, which holds all of that additional information, just to see how every other station fits. And if we know the critical station, and he's our highest, demand of everything, then anything underneath that we know will work. And that's why it's less important that we know every single one, but we know for fact this is the worst critical station here. So here's our flow that is cross-checking, and then this is our critical station that we need at the point of connection in order for it to run. And so again, what are those residual pressures? Am I in my buffer that I really want? And again, that really is up to the office to decide how much are we willing to have left over. But as long as it's a positive, obviously we're on the right track. So as we get into it, we will be going over a couple tools here. I'm just listing them here just so that you have somewhat of a reference of maybe a familiarity with some of these tools. Maybe some of these are new to you, but the upper section will be really from like a testing and a cross check or where the information is, and that bottom section is more of a test cross-check set of things. If we have time, I want to go over just some fun little workflow methods that I've found to do that. So with that being said, do we have any questions? Oh, it's a lot.
I think that was great. We just had a couple questions, easy answers, but just Shane did ask if we do use the Hayes and Williams formula, which we do. That's how we calculate our pressure loss.
Perfect. So I think we need to remember the importance of comparing apples to apples as we test. Once we know things are lining up, if something's different, it's kind of one of those, it's different because of whatever the condition is that I've set on my system. And there's obviously the caveat to trust but verify still, but understanding that, yeah, it's different and here's why, I think is the most important thing. But we have a little knowledge-based article here that I'm going to first start out with. And then I'm not going to go super deep into it, other than I'll gloss over kind of the example 2 here. But in essence, what I'm going to show here is a downloadable little file that you can do your own little tests in. We walk through step by step of the testing, how to properly test and make sure that the information that you're seeing is lining up with maybe the pipe charts or whatever it is. As we get into looped systems, this does add a really big complexity to things, especially with how many loops there are and where they are in relation to the point of connection and that kind of stuff. But this is a very step-by-step process of showing that example. And so this you can walk through in the test file that we're going to go over to see how the system's actually functioning with the different paths and lengths and stuff like that. So just know that this is kind of where I'm going the first of it. So we'll jump right over to CAD. And this is going to be what you see here. You actually will not see this in the downloaded file. This is just for our reference, so that I can compare with a chart right off the bat here. So there's definitely different ways of setting up test cases. And I think it's really important just to understand what our end goal is for what tests that we are producing. So in this scenario here, we're just trying to figure out, okay, how is the system sizing it the way that it's sizing it, the pipe itself right here. So what are the ultimate things that I need for that to happen? And that is obviously a comparable length. So we're doing this in a 100-foot span because that's what the pipe charts are going off of. We need to make sure that we are cross-checking it and using the proper actual pipe class itself so that we're looking at this. And in my PowerPoint, where we talked about pipe and the importance of that inner diameter, I will tell you right now, there are so many different varieties of inner diameters, even in the same pipe class and different schedules. They're slight, but when you're trying to get a apples to apples comparison to see what the total friction loss is, okay, yes, it's doing that. It is absolutely comes down to the decimal place for those tests. So just understanding that if you're getting any kind of varied result than what you're trying to test, it could be the coefficient, could be the inner diameter from like a 0.001 decimal place. So the velocity by a decimal place, those 3 different little spots really are where we're going to try to focus and try to harness exactly to line up with this. But you'll notice that I haven't placed any heads. If we're not familiar with what a cap is, A cap is an auxiliary piece of equipment that we offer in here. It's just right here, this cap. And if you add one of those, it basically assumes a specific demand that you give on it. So set of flow, set of pressure, you pipe to it, the system will size based on that demand there. So our little quick down and dirty example here, we are going to just use that cap for that purpose. Makes it really easy for us to alter if we're looking at this chart and trying to test another range of flow. Really easy to actually just double click on that guy and change him. But we're going to focus on this one because it has a couple whole numbers that we're going to kind of focus on so that you can see. So in this case, what we want to do, just from like a making sure that the system's good, and I guess I should preface this too. Let me go ahead and show you this new flow zone. I forgot I wanted to show this to you. So in the size pipe section, we have this flow zone option. And this flow zone option has other uses down the line, especially in golf course or larger designs that you want to limit flow in specific areas and still let a lot more flow when you're sizing the main line. You can always click more info to get like the full down and dirty on this thing, but we're going to use this tool for our purposes here today as just a cross checker, just to see, just a calculator, just to see what it is. So if we typed 26 GPM and we had that velocity set at 4.2, you can see right off the bat that it is kind of following this. So what if we change this to 4 gallons and a 4.5? You can see he's 3/4. Okay, why is he only 3/4? Well, what happens if we speed it up just a tick? Just a tick and it size. So right within this decimal place, here's where we're starting to see a potential difference, whether it's the inner diameter of that guy that maybe is different than my pipe, or it is simply and they rounded it, and maybe it's really 4.51. Well, 4.5 is less than 4.51, which means it's going to bump it up to the next size. So you have this range that you can start seeing what this is planning on doing at the different speeds for that different flow. So that's just like the diameter calculation is what's my flow, what's my velocity, here's my calculated pipe size. So that's just that little tool here. So same thing then applies really when we're looking at sizing this lateral pipe. Okay, so we have a little bit more that we're looking at in this dialog box than the other one, but it's all the same information. And this one's going to be very simple because we have a single pipe run. But you can see that if we were to look at the friction loss here, and so there's a couple bold numbers here, and I think it's good to note that these are our important numbers. Here's where we're starting from our design pressure itself, and we're building off of this for what we need back at the valve. So if we start at this number and we know what our speed is for this fixed amount of flow, we know that it's going to generate a set of friction loss. Okay, and just like reading through the book, if I were to follow along here and find 4.2, I would know that I'm sizing that piece of pipe at 1.5, and I would be losing 1.86. And that's what that is. Now, why this friction loss would be different is if something changed in its conditions, right? Maybe I shrunk that up like that. Well, now I only have 1 pound of loss. And why is that? Well, because this 1.86 is based on 100 feet, right? So it is calculating it based on the distance and on those other conditions. So if we can set it up exactly how we have it in the chart, it's going to be much, much easier, apples to apples, to know that the system is sizing it appropriately. So maybe I want to just double check it a little bit more and say that I'm going to try to do it at around 5.7, just to see if it's going to really change this 1.5 inches down to 1.25 inches, right? So if I start speeding that water up, right, nothing's happening because it's within that range of its inner diameter there. And soon as I get past that point, okay, so at 5.8 here, so 5.74. So this is under that number, which means I'm still fine. And as soon as it hits that 5.74, which our only option is 5.8, you can see that now he's adjusted. So I know right off the bat, this is finding the exact size of pipe, even based on this chart here. And again, knowing that I'm stuck in this horizontal position here because my flow is fixed. The only thing that I can change here along any of this is how fast that water is going to how it's going to size that pipe. That's where it's sticking. So if I were to speed that clear up, the smallest I could get is 1.25 inches because I can't go up to 10 feet per second. And I wouldn't want to, right? If I slow it clear down, I can see that I'm starting to get into those larger sizes. So that concept of slowing the water down increases your pipe size. It's because it's getting less friction loss and the water is moving much slower through those pipes. Okay, so with that being said, we know that this is now calculating correctly. So I could essentially do really any form of run and a flow at any point and know that the system is cross-checking that. Once we get into those looped runs, same concept applies, but we're now starting to go, oh, you know what? It's splitting the flow. And here's the difference in what we would typically do when splitting flow around a loop line is we just go, you know, I'm going to split everything just in half. I'm just going to cut it in half. Well, that sort of works. But if you really think about it, and this is how we've kind of thought about it, is which path do you think is going to get the water first, or to this point right here? Well, it's got to be the shortest path, right? There's going to be more water that hits in this run than having to make its way all the way around this way. So what the system is doing is it's splitting from a flow perspective. We'll just edit the equipment so you can see here, this 26 GPM. Well, I've got 17 here, so half of 26 is 13, right? So that's not 13. Well, that's 8. So it must be doing something. Why is less going this way? Well, we've basically taken the path distances and we've created the percent of the length or percent of the flow that gets through the long run versus the percent of the flow that gets through the short run based on their length distances. So it's calculating those numbers based on that, and then it's calculating the losses based on that demand of water. So it's sizing it appropriately for those cases there. Now, I'm going to pause right there before we kind of move to the next thing. Is there any questions? Do we have any arguments to where we're at now, Jer?
No, nobody's arguing yet. Just trying to get no, they were going great.
Okay, cool. All right. Now we're going to jump over here, and my hope is that we can start pinpointing now from the assumption that, okay, we've done a project, we've verified everything, and I can't stress enough, like just in general from a workflow perspective, that as you verify a system, that you're doing this periodically through the design, making sure that you've got all your unpiped heads checked, and on the verify mainline side of things, that we are making sure that our lateral pipes have been sized and stuff. And the importance of that, obviously, is that we want to make sure that we're accounting for everything before we start making those final decisions on sizes of stuff. If we've sized our valve and we're missing some heads, or something wasn't connected properly, well, then that valve number is incorrect, which means when we size our pipes or our main line, those are going to be incorrect. So the verify step is super, super important on this. So we are assuming that everything is good, ready to go. And then one last check, as you are sizing the system, I also can't recommend enough where we do have the size all option, to where, hey, I can just size every single valve. And that's, in certain circumstances, really nice, because it quickly gets you through and it sizes it appropriately based on some simpler conditions. However, I can't stress enough that you should be going zone by zone to actually pull up the size lateral dialog box to make the right decisions on what you got going on here. Now, the reason that we do it this way is because once you size it and maybe you do make some alterations in how the system is performing with that zone, it saves that velocity for that zone. But if you size all, it wipes it out and it kind of blanket applies the speed for every zone, which, again, depending on the scenario, is okay. But sometimes different stations require a slower speed in order for them to actually function. And that's where this actual velocity comes into play. So the actual velocity more than likely is going to match whatever we got going on here. And let me try to get a little bit bigger of a zone here so that we can see this in action. Your pressure variation is somewhat of a, call it a safeguard for you not going too high in pressure loss or in friction loss. So if you've got a system that maybe doesn't have the greatest pressure to start with, maybe you don't want to allow the zone full on pressure losses based on the speed of water. So you might be running something, and I, again, wouldn't recommend this, but just for our purposes, you can see that this is actually changed. And because the system with this pressure variation put in place has said, hey, you said you don't want to lose any more than 6 psi. But if you go past 6.5, you're going to do that. And so it's going to automatically size you down to fall in range with this pressure variation right here. So you're welcome to slide this down to the left and turn it off, and it would say, okay, I'll let you do whatever you want, but it's going to cost you pressure. So we'll go ahead and slow that down. You can see there's never going to be a time that the actual velocity changes. That obviously changes what our pipe sizes are going to be. But if I set this pressure variation too low, I'm going to have a problem. And so when, just in general, if you're sizing all valves at the same time and you have this pressure variation set to where it is blocking a valve from working, this is the message you're going to get. It's going to say, hey, I've tried slowing it down, but I can't get to that. Maybe you need to adjust something, kind of a thing. So the size all does impact, what the system's looking for from a velocity perspective, because it will auto change it if it needs to. But if you're setting that limitation, it's gonna cause a problem. So we'll go ahead and set it for whatever it is. Let's find out where that is right here. right here. So if we set that pressure variation, you can see that the system's going to say, hey, you need to slow that water down so that it doesn't breach that. And this percentage, by the way, is a percentage of your design pressure. So set it if you want to have those safeguards in place. Turn it off if you're, loose and willy-nilly on things and don't care how much friction loss you got going on. Go ahead and do that. So just know that if this is off, the velocity is going to be the determination on really how much friction loss you got going through the pipe. Obviously up to a certain point, right? There's the flow itself, no matter how fast you go with that, is only going to go, so much based on the size of pipes that you have available. So it'll change in relation to that. So from there, our fittings factor, again, is just a little additional play in some friction loss. So you can see that I'm 10%. It's adding 10% more allowance or buffer for the losses that happen through the fittings there. Again, doesn't make a huge difference a lot of times. So when you're trying to save pressure and stuff like that, I wouldn't really adjust this. I would definitely keep that into account there, but because it's really not going to do much for you. There. Obviously, our elevation is an additional thing that we got to consider, right? So is there elevation to the plan? Being able to manually set that right here is going to show us what that additional loss is. If there's spot elevations in the plan, this will be allowed to be checked, but we don't have any at the moment, right here. And then the last thing that we're considering is the loss through the valve. And this loss through the valve has everything to do with the performance data of the valve itself. And so I know a lot of people have questions about the drip kit valves and the losses that are happening through there. Essentially, the losses that are happening are, according to the manufacturers, a pressure differential, and we are only able to put in that as a loss because that's the information that we have. So we'll get into that in a little bit if we need to. But that's where the loss is. So this pressure required is that furthest head back to the valve, including all of the friction loss, the design pressure, the valve loss, and everything. So that is what is needed for that valve to run, or those heads to run at that valve point. Okay, so that's what's happening through this. Do we want to pause for 2 seconds and just see if there's any questions there, Jer, or are we good?
We're gonna got a few questions stacked up that I'm answering now, but I think you can certainly keep going.
Cool. So that's just my little plug as far as, okay, you've gone through things and you're sizing stuff. Just make sure you're kind of aware that that's how we should be doing it. Size all is great. I love that one. But it's a little dicier is all. All right. So before getting too much further in here, I really recommend running a valve schedule. Okay. And this valve schedule just is such a good snapshot as I've got it set right now, before even sizing the main line, before getting into troubleshooting what I might have wrong. I do enjoy seeing everything. I check on everything just so that I know what I got going on here. So I'll go ahead and just check everything. Now I do have specific work areas, which is limiting what the system is looking for. I've got a secret other place up here that we're going to do something for. So I'm looking in this area specifically, just so you know. I'm going to click on that work area and I'm going to run this valve schedule. So this valve schedule, and we'll kind of break this down right now. It just obviously gives us a snapshot of how the system's set together right now. Can't stress enough, the importance of a valve call out. Okay, so if you're not calling your valves out, maybe you're waiting to the very end, you're kind of doing yourself a disservice, because that valve schedule, if you just see a bunch of unknowns everywhere, it's really, really hard to know where to look for stuff. And especially from a troubleshooting standpoint, and sending in the files for help on anything, we're going to recommend that you label your valves so that we know where we're looking, instead of going the valve that's over in that one area. So label your valves. This gives you that snapshot of not only the type that it's watering, based on your equipment itself, but the total flows, the head count, which sometimes is important, sometimes isn't, but it's just fun to see, how big of a zone, this turf spray guy is right here versus one of these guys, and why is that kind of a thing. Because that sometimes affects why you're getting, too high of loss or too low of loss. You can't have too low of loss. But the design pressure, right? So this is a really important one here. This design PSI column is such a good number to cross-check, because as we're setting up and discussing our water source, that design pressure should not be close to what we got. So I can run this valve schedule, and I can look at my source data, because I guess I haven't really looked at that totally. Okay, looks like I have 45 PSI available at my source. And really, after the loss through the water meter, I've only got 44. And so, whoa, that's a low starting point. I already see red flags happening here. So if I'm looking at this design pressure and I see these set at 40, well, heck, I know that that's at the design pressure stage. What is that doing at my actual valve itself after sizing that lateral? And I can see I've already exceeded 48, 48, 43. So I've already cross-checked myself before the system has stopped me. So this is just such a good way to start addressing stuff before it even happens. And again, knowing that design pressure from the equipment selection point is such a key thing, to know, okay, we've got low pressure. Guess we can't use higher or larger demand types of heads, basically, right? Or maybe we do, and we start talking about a booster pump itself. So that's the kind of stuff that I really enjoy looking at here. The friction loss is obviously important from the lateral pipe sense. So we can start to see, oh, wow, I've got quite a bit going through some of these, and why is that, right? So I can see that these are some of the higher flows that I have some of that higher friction loss on, and what can I do to remedy that? Maybe I can't. The valve loss, I think this is one of the bigger points, just in this whole grand scheme of things, is why is when I'm sizing this thing, why is it saying that it's the critical station? And it really comes down to obviously the ultimate number of PSI POC here. So we'll get into that next. But I like running that valve schedule. It's just really going to help show how things are. And now we're ready to size the main line. So we'll go ahead and size this main line. You'll notice that at the command line, select a water meter or POC or all. If you're in an instance where you have multiple water meters, I really would recommend clicking on the one that you want to size. It's just going to be much easier to see where the errors are happening, instead of assuming, which one has bombed out and why. So I'm going to go ahead and pick my water meter. And I have a little simpler box than that size lateral. And the only thing that we care about is, well, 1.5 things. Whether we're doing a single valve at a time or multiple valves at a time. And the reason that's important is because that's setting our flow benchmark, okay? So when we talk about the size of pipe, we care about two things. We care about our flow, and we care about our speed. And that tells us what size we can do. So if we are sizing one valve at a time, this little grayed out number is showing us that this is the highest flow out there, the highest demand of flow, and that's what it's going to account for as it sizes the system. Anywhere else that it hits a branch that doesn't need that, obviously it will size according to that highest flow, but in the system itself, this is the number that it sees. If you choose multiple valves at a time, this number changes, and this number changes to your available flow from your source data. So it's saying, hey, go ahead and use all of what's available for what it is, and it'll combine as much as it can valve-wise up until it hits this number. So if you want to be, call it safe on it, and maybe set it just to more of a limited amount, you're welcome to set that here. This is kind of like that flow zone dialog box, right? I get to put in my flow, I get to put my speed, and that's really calculating what that size is anticipating to be. So the system will take that that 50 gallons and start adding different valves up until it hits that number, and only go up to that amount. So we'll just do single for now, and we'll leave it at 5 feet per second. We're not going to choose any elevations, and we'll go ahead and say okay. So if we get this message, what do? Pressure available at the point of connection has been exceeded. What do you want to do? Do you want to try to reduce the velocity, or do you want to just stop and address it yourself? Okay. So I like saying yes to this, because what this is going to allow me to do is slow that water down and start seeing if it passes based on just increasing the pipe size, because that's what we're doing. So I'll say yes. The system's only going to go till 3 feet per second. As soon as it hits 3 feet per second, you kind of sort of assume you're not going to pass, because if it stops it here, then we know that something is probably lower than that, and you got to kind of address it from there. I will suggest that you say yes to this, at least until you start understanding what it is, but it's going to highlight those valves that have the exceeded requirements. Yes, you want to see more information. This is going to kick you over to our documentation page that kind of walks you through how to troubleshoot that more. I am going to say no, because I know what I'm doing. And we've got this critical analysis, and this critical analysis is not complete. This is sort of a stopping point to say, hey, here's where I stopped you. You can go now figure out what's going on. And so all I care about is this lower section. This lower section, we can go ahead and see that I got 50 PSI required. Well, obviously I only have 44 available. Take into consideration all the other losses through all the other pieces of equipment. I know I'm well over. I need 71 instead of 44. So what do? Where is that critical station 50 PSI? It doesn't even tell me a station. And so there's something in here that is requiring 50 PSI. How do I find it? Well, our locate valve command, I type locate valve, it's in the station tool set, right up here in the station. But locate valve allows me to select a POC, or I can right click for all. And now I can look for, and I'll filter it so that it's in gradual order here. I can see there's the 50 that it was looking for. And there's no number here. Let's see what it is. Found it. It was that cap right there at the end. I was anticipating for future use, I wanted to size up so that I had a certain amount, but it was just too much. For our purposes and speeding this along, I'll go ahead and erase that, and let's go ahead and just try it one more time. Size that main line. All right, so still got it, still hitting everything. All of these valves are exceeded. So now I know for a fact I'll probably have to start looking at a booster pump because I don't have any big ticket equipment things in there. So let's go ahead and just insert a booster pump. Auxiliary, I've got a booster pump already added. We'll just go ahead and place them in here. BP. And when I add a booster pump, it's obviously giving me that ability to set what my pressure increase is and the max flow that pump can handle. So we'll go ahead and try to size that pipe again one last time because I've increased my pressure. I know I'm good now. Well, looks like I got a different message this time. And this one's just fun to just be aware of, that it has identified valves that have flow requirements higher than what I actually put that booster pump allowed flow to be. So it's telling me, hey, there's a certain few of those that are actually exceeding what that is. I can identify where those are. Yep, it looks like those are some pretty high flows. Maybe I can edit that piece of equipment, that pump, and say, oh, yep, I only put it at 15. I should probably put it to the right number. And let's go ahead and size. So with the pump pressure increase, the flows to be right, you can start to see that the system is sizing those pipes now. And if you ever get that error and it bombs out, it's not going to finish sizing the pipes, just so you're aware. All right, we have a positive critical analysis here. We can see what critical station it's finding and the breakdown of that stuff. And so this little first section, loss through or pressure required at critical station, is that valve required PSI. Loss through fitting, mainline, elevations, backflow, master valve, water meter, all of that stuff is through that main line down to what it's cross-checking. So what I need at the point of connection. It's then cross-checking against what I have available, and it's giving me a residual. So if I were to rerun now my valve schedule, this PSI column is the valve PSI. And now this is, once you've sized, the PSI at the point of connection itself. So we can start looking and seeing the breakdown of what each valve is required that way. Okay. Okay, from there, see where I got going on here, running out of time. I want to go over then just one other thing. We're gonna jump to another situation. Here, I'm gonna run a new valve schedule. This area right here. And if there's elevations involved, so this guy's is on a big slope here. We got elevations in there. It recognizes some specific elevations here. Some of them look pretty decent. Some of them look really far off. And again, when we're sizing stuff and you're getting this, hey, this has exceeded your stuff, I obviously can, again, just go ahead and size this pipe or size this main line right now to say, all right, I think I'm good. And I can say, yeah, reduce that velocity. Okay, why is it bombing out on me here? And I can look through. L10 has a pressure requirement of 452 PSI. Well, we know that's not right. So how to find the issue there? Obviously, I can use locate valve to find L10. I kind of know where he is. But why is he so wrong? And I can use highlight station. I can click to see where he's at, but I might not be able to find exactly where the spot elevation is for that issue. I don't know what I'm looking for, right? Well, it's looking for the furthest head to the valve location. So I can look at either end of that to see where it is. And oh, looks like that's where it is. It's catching that spot elevation. So if we were to change that guy to what he probably should have been and resize that valve itself, it's going to fix that elevation. So that's the important part. If you're fixing something out on the site, it's very, very important that you go back into here and resize that zone so that the system can actually take into consideration what it's actually doing here. So we're going to do one last thing here, show off the mainline profile. So this is a really fun tool, and we'll be releasing it into the ribbon in the near future, or our next release of the ribbon, I guess you could say. But this is just a really fun tool to identify certain things here. So if I go ahead and just for our purposes, I'm going to change this here. I need to make sure I see which one it's going to hit first. It's this guy here. So we're going to change him to 1100. Maybe I had a mistake here. And L6 was identified as too high, and I didn't know where it was. Mainline profile. Type mainline profile. And click your point of connection if you have multiple. And then an end node. I'm going to pick L6 here. Any connection along the main line allows me to run a schedule, a profile of this with its elevation. So I can click that schedule in, and the system's going to chart out that path up to that point, including its elevation. So this is an elevation profile. So from the point of connection, its spot elevations, it's going, and then I've identified, whoa, that's the marker. It's an 1100 foot deal there. So I can essentially know which spot elevation number I'm looking for. So now I can do a find. I can look for 1100. It found that 1100. I can change it to whatever I need it to be. And if I were to run that mainline profile again, here, go here, right here, you can see that it charted it out appropriately for those elevations. So this is just a really other cool way to cross-check, especially from like a distance and a velocity and what you're getting friction loss wise and stuff for the lengths. I clicked from the point of connection to a valve, and it tells me my overall distance for what that is. And I can basically do the calculations from elevation loss, friction loss, chart that way. So I know we didn't leave very much time, and holy smokes, can we do calculations all day? But Jer, are there any last questions?
Well, we had a really nice little sort of lively back and forth regarding the friction loss for drip emitter areas.
Mm-hmm.
So definitely that was really interesting to consider, what we can do more to calculate some additional friction loss there.
Cool.
Also work around for that, and also pointing out for the spot elevation for a valve, the little trick that you did, drawing a circle from the valve.
Yeah, I
And
did
so then,
that on without knowing. That's a good one.
yeah, that's a good little trick. All these fun little ones. Oh, and then just, another really good comment here, that just popped in from Michael. If you're able to touch on the pressure losses through the drip control kits.
Yeah, let's do it. So the drip control kits themselves, so we'll go ahead and let's just run a valve schedule here really quick. Okay, so I have multiple point of connections in this drawing, so there's a lot of different set stuff, but we can see that we've got a couple right here. Valve loss 10, right? 2, 3, that's fine. Tens, a lot of tens. Okay, why is that, right? So I can go to any one of those valves. I'm going to use locate valve because it's my favorite tool. We'll go to H1. There it is. I'm going to edit that piece of equipment. Here is a little deeper dive too into any one of these that you're looking at. Is there is an analysis button. If you use edit equipment, click on a piece of equipment or on a valve specifically, you're actually given a little breakdown of what it was sized at. So we know it is using 25 psi as its design pressure, so that equipment set properly. The friction loss is loss for the valve. Okay, so that's, we've identified that guy right there. It also shows me some probably incorrect precipitation rates, but that is drip area, and you and I need to talk about that, Jer. But we'll go ahead and use that view data button now. Let's call up that actual chart for what this is. So let's go to our which one is it? The ICZ 101. So the ICZ 101 is right here. Now, here's what we need to consider is this is all the information we're given. So if you have any problems with the numbers that you're seeing here, it is highly recommended that you reach out to your manufacturer to get any other clarification on this, but this is how we have to address it. So zoom in here just a little bit. So required pressure for a 25 psi outlet. So if we want that thing to operate at 25 psi, then we need a certain inlet pressure. Now, if we just take all equipment out of the equation and we're talking about from furthest head back through the valve to know what we need in order for this zone to run, we can just assume that this is a loss. Now, this loss is considered a pressure differential to the manufacturers, which I'm still questioning what the difference is fully. Unless we get different numbers, this is what we have to consider a loss. And so for it to operate at 25 psi with 2 GPM going through it, it needs to have 35 psi, which is a 10 psi difference. So what that means is you should be looking at it from the standpoint of, is that the right size of valve for you to use? You know, maybe you have a different kit that you can actually look at that has a different range of inlet pressure, inlet required pressure, or a different flow set. So if you're using a high amount of flow, I don't think this one is the appropriate one, right? We should probably go for the larger, the 151, or one of those other larger size that start at a higher flow that would have a lower required inlet. So that's really what it comes down to. So if we're looking at this, we already know that that zone has 1.38 GPM. So in the chart, we can see the 1.3 GPM here is basically, where we go, starts at 2. So that's where we're starting our chart from, is this available 2, which is the 10. And so it's pretty easy to determine, okay, this is how much I can anticipate losing because I need to make sure that I have that available for the system to actually operate that. Now, if we don't have that to begin with, if we have lower pressures, there are several different things that could be done, but specifically right here in the charts, they say, hey, if you have any kind of starting pressure or working pressure below a certain point, you might not need the regulator, right? So just understanding that pulling that regulator out, filtering it properly, using that same standard valve that's coming with the kit will sort of remedy that. And it's just something that if you have questions with, issues with, the manufacturer is absolutely willing to hear that, and so that we can try to get information more appropriately put in. But that's literally all that it is. Okay. I know that was a long-winded answer for that, but hopefully that
No, it was good. It's part, and I
helped you.
think it's it highlights just so many things. I mean, it highlights that our challenges with interfacing with the manufacturers and getting this data right, but it also just highlights just the overall efficiency of this whole endeavor that we're doing. Instead of having 1,000 different irrigation consultants all individually calling a manufacturer trying to figure out, is it pressure loss or pressure differential, it's just us interfacing with that manufacturer, where this, it's all the benefit of a middleman, if you will, right? And it's just like there's certain times it's very convenient to have a middleman so that the manufacturer is not slammed by all these end users all having to replicate the same thing. So I just really think it really shows how helpful that is. And as we talk more with Hunter and other manufacturers on perhaps a better way to illustrate it or show it, then it just goes out in an update and everyone benefits from that. So really cool. But hey, on that note, we are over time. Thank you guys so much. A few people have already chimed in and said they really enjoyed it. Jake, fantastic job. Everybody have a wonderful weekend. We'll see you next time.
Thanks, guys.